Syzygy Season 2, Episode 4, Exoplanet Extrapolation. And welcome back to another episode of the Syzygy podcast in special Season 2 Exo Edition. I'm sitting in the office of Emily Brunsden. Emily, how you doing?
I'm well, thank you.
Good. Now, we are doing a series on exo things, things going around other stars that are not our own. We've covered so far exo moons, exo comets, which still blows my mind. I can't believe that we can actually see those things. And we talked about exoplanets, current state of the nation of exoplanets. We're going to do a bit more on exoplanets today. I mean, let's face it, if you're going to do a series on exo things, exoplanets are going to form the meat of that particular feast, I guess.
They're the OG exo things, aren't they?
They are. But we're going to go in a slightly different direction today. So, Emily, what's the plan? What's the episode today? Where are we going?
Well, as we say, last time we did kind of state of the nation and we talked a lot about finding exoplanets, which we've established we're very good at.
Yeah, pretty good. We've established that one. We know how to do it.
Yep. Today's much more about characterization of exoplanets, with a very special nod to a very wonderful space telescope.
Yes, the JWST.
A just wonderful space telescope.
Just wonderful. Yeah, James Webb.
Yeah, that's right.
Yeah. And, of course, that's one of its big mission priorities, isn't it?
Yeah.
It's not its only one, but it's a big one.
Indeed.
Yeah. And so when you say characterization, we're moving beyond... Can we see them? Can we find them? Yes, established we can do that really quite well in a bunch of different ways. But this is now, so what are they like? Right. So we'll go through maybe a few different things that we can learn about exoplanets.
Exactly. Yeah. But I thought it might be better to just give a quick recap on James Webb, the Space Telescope. And what it's up there, what it's doing, and why, basically, what it's looking for.
Sounds good. So, a JWST recap.
Yeah.
Let's go.
So, JWST was launched 25th December, Christmas Day, 2021.
It was. I remember it well because I was in a lovely house in Wales with my family and we all had COVID.
Right.
On Christmas Day. It was horrible. It was the worst I've felt in a very, very, very long time. And I could not get a single person to get excited about the launch of JWST with me. So I sat in a corner feeling awful, watching this thing lift off and going, please make this happen. Come on, kids, come and watch. No one cared. But I cared. It was very exciting.
Yeah, well, I was at home. I was mid-second trimester, and I was trying to pretend that the alcohol-free champagne that I had tasted as good as the original.
Yes, well done. Yeah. Well done. Gosh, that does seem a long time ago.
It was a long time. So, nearly 3 years, in fact, coming up next month. It is, in fact, the largest telescope in space. Still holds that record with a 6.5 metre mirror. So, for comparison, I mean, James Webb has often talked about the sequitur to Hubble. It is and it isn't. I think we can go into the details of that in a different episode. If we haven't already, we probably have.
I think we probably did when around that time when it was taking off. I think we went into some depth on that. So go back and have a listen to that one. But it's quite a different telescope. Yeah. To Hubble.
Main point is that Hubble's 2.4 meters, so James Webb is a lot bigger, but Hubble works in the ultraviolet and the optical, whereas James Webb works in the infrared.
So they're looking at quite different parts of the spectrum, and so they can see different things.
Exactly. Yeah. So even though James Webb is a lot bigger in terms of its mirror, it's actually similar resolution to Hubble in terms of the images it produces.
Okay, because your resolution depends on your wavelength. And so to get the same kind of resolution in infrared, you need a bigger telescope anyway.
That's right.
Yeah. So these two are complementary, is what we're saying.
Yeah.
Yeah, good.
So it's been around nearly 3 years. Now, as you said, one of the key science goals of James Webb Space Telescope is to look at exoplanets, and in particular to look at planet formation. So we talked a little bit about that when we talked about the exocomets, actually, and also to look for origins of life. So those are probably the two strands of the key mission goals that we're touching on with these exoplanets.
Yeah, digging a bit further into this whole field of exo things and going beyond, yes, we can see them. Now, how much can we learn about these things? And as we saw in the comet episode, there's a lot that you can see, beyond just there's something going around that star. We can learn a hell of a lot.
Exactly, yeah. And that's where James Webb is very, very different to, say, Kepler and TESS, is because its main approach is about looking at the atmosphere and maybe even eventually surface compositions of these exoplanets rather than just are they there or are they not?
Right, and doing that through presumably looking at the spectrum of light that we're seeing from these things and seeing, what's other than the light that's coming from the star, which is obviously dominant, what else can we see and how would we explain it?
Well, there's 4 kind of ways that James Webb looks at exoplanets. And so I thought it might be useful just to recap all those because they're important for some of the individual star planet systems that I was going to sort of just talk about as kind of cool examples as well.
All right, let's do it then.
So the first one is transits. And I'll pull this one up first because it is the same technique as what we talked about last episode.
Yeah, and we've talked ad nauseum over the years about transits, planets going in front of stars causing dip.
Yep. So James Webb can do that just as much as other telescopes can. It's not really its main specialty, but it can do it, right? I'm going to give a couple of examples in case you want to go and do some homework and look up some nice case studies. But the TRAPPIST system, we've observed the transits from space just as we observed them originally from ground-based telescopes as well.
Sure. Put a link in the show notes.
Yep. So an extra exciting version of transits is James Webb is capable of doing full phase curves.
Full phase. So what does that mean?
Right.
Explain that.
Well, have you ever seen the phases of Venus?
Are they different to the phases of the moon?
Well,
I feel like we've talked about this before, but my brain's quite full, so remind me.
Okay, so the moon has phases, right?
Yeah.
So because the moon is going around the Earth and different parts of the moon are illuminated at different points in its orbit around the Earth.
Right, so sometimes it's a full moon, sometimes it's part of a moon, and sometimes it's no moon at all, even though it's definitely still there. It's just which part is facing the sun.
Yeah.
Yeah.
Actually, geometrically, I find it much easier to imagine the phases of Venus, because Venus has phases. And you can see them if you look through a small telescope, because Venus, just forget about the Earth, Venus is going around the sun. And so from our point of view, sometimes it's kind of between us and the sun, and that would be an eclipse or a transit.
Sure.
Right. And then sometimes it's off to the side. And when it's off to the side, you see half a lit surface of Venus. So it looks like half of Venus.
Yep.
Right. When it's round behind, you can't see it because it's hiding behind the sun. And when it's on the other side, it comes half again. So you go, and just before it goes behind, actually, it's a full circle of Venus that's illuminated by the sun.
Yeah, I mean, obviously, if it's actually behind the sun, we can't see it. There's a sun in the way. That makes sense. But just before that, if you sort of sneak a look past the sun, you'd see that full, the equivalent of the full moon.
Yeah,
right? Yeah,
full Venus. Yeah. And so if you were to measure the amount of light that came from Venus as it's reflecting off the sun, from the sun off Venus, you would see at new Venus, let's call it, no light, because that would be when it's in between us and the sun. So you won't see anything. You get half Venus, right? So it comes up, it gets brighter and brighter and brighter. You get half Venus, then it gets brighter and brighter and brighter again to full Venus, and then it drops back down to half, and then it drops back down to new Venus.
Sure. So all very familiar from phases of the moon, but you could do it with Venus as well, because Venus is between us and the sun in its orbit, and so you're going to get those same...
Yeah, so Venus changes in brightness over the course of its orbit.
Cool, okay.
Exoplanets
Turns
do
out,
exactly the same thing.
Right,
Yeah.
and you're not looking... I mean, we think of phases of the moon as being specific shapes, but you're now thinking of it in terms of changes in brightness.
Yeah.
Because you've got, all of it or half of it or none of it. Yeah, okay.
So just before the planet gets hidden by its star, it's the brightest, and then just before it goes into transit, it's the faintest.
Right, makes sense. So if you think of that in terms of like a transit episode with an exoplanet, whereas before we were just, can we see a dip at all? You're now talking about, am I right? You're now talking about, how much light are we seeing reflected from this thing itself? And you can actually track that.
Yeah. These are called phase curves. Yeah.
Wow, that's amazing. I mean, again, that kind of feels a little bit like the comets or the moons. Like, that's surely so many orders of magnitude smaller than just detecting a planet at all. That's impressive.
It is impressive. I mean, to be fair, we're good at detecting it for the easy cases, as always, right? So where you have a very large planet that's very close to its host star, hot Jupiters are going to be part of this. And some of these planets are, just a substantial fraction of the size of their host star. So the amount of light that they're contributing to the overall system
makes sense.
Is quite significant.
In the same way that the first exoplanets we detected were the big honking ones really close to the star, the big honking ones are the ones that are going to be sort of, casting off the most light as well. Yeah. So what does a full phase curve look like? Is it kind of like a sine wave? Is it sort of sinusoidal? What do you...
So, yeah, I mean, you could look at it as a sine wave, but then you've got two blips in your sine wave. One where this planet moves behind the star. Yes. That happens at the peak.
Yep.
And then one at the trough where the planet moves in front of the star. Mm-hmm. It's because you remember you're always talking about the sum of light from both the star and the planet.
Right. Yeah. That makes sense. Yeah. That makes sense. Cool.
So if you want to have a look at a nice example of a phase curve, GJ...
Which we do, yeah.
Then GJ1214b would be a nice one to look at.
Okay. Well, I'm hoping that is currently displaying on your podcast player of choice as the chapter art for this particular chapter. So go and have a look.
So there's phase curves. Mm-hmm. Then we have transmission spectroscopy. This is probably the most famous part of James Webb's sort of planet characterization ability. Mm-hmm. So this is where we're using spectroscopy to figure out what the components are of an exoplanet's atmosphere.
Right, okay.
So we're quite good at using spectroscopy to find out what the chemical makeup is of a star's atmosphere. We've talked about that.
Talked about that loads of times. You look at the spectrum and you can see the fingerprints of all the different, atoms and molecules and species that are in the atmosphere of the sun. You can see what's there. Yeah.
So this is using that technique, but just implying a really cool sort of add-on to that, which is when the planet, which has an atmosphere, passes in front of the star, some of the light from the star gets passed through the atmosphere of the planet, through the edge, if you like, of the atmosphere of the planet. So where there is absorption happening, so there's gaps in the spectrum because of the chemical species, what you do is if you take a spectrum of the star on its own without the planet there, then you know what the star's spectrum looks like. And you take a spectrum when the planet is in front of it, then you know that any difference between those two spectrums.
See, I'm shaking my head. I've seen pictures of the Earth, Emily, and I know how thin our atmosphere is. Like, it's kind of disturbing when you see pictures from space of how thin this layer of protective atmosphere that we depend on the Earth is. Like, we think of it as, it goes all the way to space. Yeah, that's only like, what, at most 100 kilometers? 60, like, it's nothing in comparison to the size of the Earth. You're telling me that apparently we can see the effects of an atmosphere of a planet as it moves in front of another star. Like, you want to talk about tiny effects on top of tiny effects. Surely that's... I can't imagine how you would actually detect that.
It's true, but once again, remember that we are talking about the easiest ones to find, which are not planets like the Earth with our very teeny tiny thin atmosphere, but big stonking great hot Jupiters with huge atmospheres, right?
Okay, so in a case like that where the atmosphere forms a significantly greater proportion of the radius of the planet, you're going to get a lot more light coming through it, so you'll be able to detect that better.
Yeah, I mean, Jupiter's mostly atmosphere at this point, right?
Yeah, but I mean, if you were to put the sun behind it, how much light would get through?
Well, that's a bit unfair because I think because Jupiter's a lot colder than these hot Jupiters. Jupiters.
I'm prepared to take your word for it that this is possible. It just breaks my brain thinking about it. So well done. Well done, everyone.
So we're quite good at doing it for hot Jupiters and getting some idea, at least of some of the molecules that are in the atmospheres of these big hot Jupiter.
Yes.
And again, your sort of nice example is WSP-39b. If you want
We've
to have a look at that.
We've come across WSP-39b before, I'm sure.
I can never remember the numbers.
I don't know.
Maybe we have. Yeah.
Again, we'll put the link in the show notes.
Yeah. And then the fourth one, so we're up to number 4, the way that how James Webb can detect and characterize exoplanets is actually through direct imaging. Mm-hmm. Now, this is quite a hard technique.
You surprised me. Actually looking at a planet, yeah.
Yeah, I should have probably prefaced all of these ones with this. But anyway, it's actually particularly hard for James Webb because of the light that it's looking at. It's looking in this infrared light. which means that some of the best candidates to find with direct imaging have host stars that are very bright and actually completely swamp out. Their brightness is just too much. It swamps it all out. But James Webb has got 2 instruments, I think, now, which have what we call coronagraphs on them, which is, it sounds very fancy, but all it is it's like a bit of paper that you hold up to block out the light from the star, and then you see what is behind it or near it.
Right. So it's just sort of, you stick something, whatever that something is, over where the star is in your field of view.
Yep.
Just where the star is.
Yep.
And that blocks out that. Like, that sounds like a very rudimentary way of doing it, but it kind of makes sense, right?
Yeah, it works, right?
Yeah.
So we can get some nice planet images from that. And if you want to see a lovely one, we've got HIP 65426b. It's a nice example.
Again, link in the show notes. Can I ask a question about that technique? Like, it's not literally putting something in the way, is it?
Yep.
It literally is. How big is that? I mean, even through something like JWST, and I know, I talk about looking through JWST in the sense of you put your eye up to the eyepiece. You don't do that. I know that. But even with something like JWST, these things are really small.
Yeah. I mean, it's not like it's actually going up, say.
I'm imagining someone sticking a red dot on the screen.
It's in the optics of the actual camera system itself.
Right.
It's in the back end. It's not in the front end. It's not a piece of paper that
no one's holding up. There's no one up there in a spacesuit holding up a little thing in front of them.
But that is how we originally started doing coronagraphs. Yeah. And coronagraphs, they're called coronagraphs because they're how we actually discovered the corona of our own sun.
Right.
Because many, many years ago, it'd be a couple of hundred at least, we figured out that if you hold up the piece of paper that's exactly the same size as the sun, then much like during a eclipse of the sun, you get to see all the lovely atmosphere glowing around the edges that you can't normally see.
Because the brightness of the sun bit is just too bright and we can't cope with that. But if you block that bit out, like with a piece of paper or during an actual eclipse, you can see the corona really well during a full eclipse, right?
Yeah.
Yeah, cool. Okay.
Yeah, so those are the 4 sort of main ways. And then I thought, actually, it might be useful to look at... I've chosen 2 and a bit.
2 and a bit. Mm-hmm.
2 and a bit sort of specific ways that James Webb has sort of contributed to some really exciting new information about exoplanets.
All right. Give us the 2 and then we'll get to the... Or do you want to do the bit first?
No, let's do the 2 first.
Okay.
We'll do the 2 first. So the first one I thought would be... It's a bit of a throwback for us. It is going back to the OG for... I keep saying that word. I'm not that cool.
You're a woman of the times.
I'm trying to be, but I'm
at
really
least 3-4
not.
years ago.
Yeah, okay. One of the first images that was released as part of the James Webb First Light series.
I remember the images coming out, but I don't remember what the images were. So remind me.
Well, there were about 6, weren't there?
Yeah.
There was,
and they were stunning, to be fair.
Well, 5 of them were. So there was the Great Wall. Do you remember the beautiful pictures? There was the Stephan's Quintet, I think. There was a group of galaxies. They were all like these really wonderful images, and there was also some really nice narrative that went with all of them, why they're really interesting things that are part of James Webb's,
understandably, some amazing PR going on here. We've just spent a lot of money and a lot of time getting this thing into orbit. Trust me, folks, this is worth it. Here, check these images out. Yeah,
but the one that personally disappointed me the most was the exoplanet one.
Right.
Because they just showed what to me looked like a fairly dodgy graph.
Like, I can make a dodgy graph. Come on.
I mean, it had a nice background, but look, I'm going to put it out there. I don't think that was the best choice for that set of images.
But was it at least showing some interesting science?
Well, yes, but I don't think the graph gave the excitement that it should have. I mean, I don't think it portrayed the message that it needed to. Okay. So the graph that they showed was a graph for a known exoplanet. It's called WSP 96b. It is about...
Isn't that the one we were talking about before?
No, that was 39b.
Oh, silly me.
Yeah. This is 96b. So it's a planet that is about half the mass of Jupiter. It orbits its host star every 3 to 0.4 days. So it's quite close.
Pretty quick.
Yeah, hot Jupiter, right? In fact, its orbit's so close it's about 1/9 of the distance between Mercury and our sun.
Wow. I mean, that's, again, just blows your mind that that's even possible. But okay, sure.
Yeah.
Turns out it is.
Yeah. So they used transmission spectroscopy. This was the big thing about James Webb. We're going to get this transmission spectroscopy. And they looked at the atmosphere of this hot Jupiter. And then they took the spectrum and they plotted a graph. Mm-hmm. Now, they're being honest in this graph, which is right.
It's good.
It's right and good and correct.
It's the right thing to do.
It's a graph that shows the spectrum of the exoplanet. And it's got all the points of where they could measure the spectrum. And it's got the error bars, which are pretty large. Mm-hmm. But I think that's pretty normal for this kind of work. And then it's got a model to fit the spectrum. And it's got some labels on it that shows here, look, these are the interesting bits. This is the bit you should look at.
We can see this molecule and we can see this molecule... asterisk to within error bars.
Yeah. And the one that they were really pointing out and saying, this is awesome, is water.
Water's good, right?
Yeah.
If we like seeing water on other planets because water maybe, big asterisk, means potential for life.
Well,
except
indeed.
Maybe not on a hot Jupiter. But it's a proof of principle.
Exactly.
We can see water. Isn't that awesome?
Exactly. And there were clouds and hazes and there's some interesting stuff that went all behind this. And so I think the science is wonderful. I think the choice of the graph and the presentation of the graph was awful.
Didn't do it for you. I get that. Can see that. Yeah.
Because after seeing pictures of Stefan's quintuplet of galaxies interacting, you don't really want to see a graph which has really big error bars, a model that to the untrained eye doesn't actually look like it fits all that well, and then to be told this is exciting because there's this little blip here that's water.
Yeah, I mean, look, to the people who are working in that area, I'm sure that was like, this is great. Like, I'm going to frame this and put it on my wall. But for everyone else, like, yeah, I see where you're coming from. It's not exactly poster-worthy material.
No, but to be fair, not much of exoplanet science is.
No.
Unless it's an artist's impression, right?
Yes, exactly. I was about to say, there's a hell of a lot of artist's impressions out there which kind of give you the impression that, wow, like, we know a hell of a lot. We know what this place looks like. We know what the creatures flying around and swimming around on the surface look like. No, we don't. We don't.
No, so it's never really going to become, your desktop background. Well, unless you're
really into graphs.
Yeah.
In which case, go nuts.
Yeah. So anyway, that was just when I remember seeing that and going, really?
Fair enough, but at least it was one of 6, right? If they'd all been like that, it would have been a bit sort of.
Yeah. Anyway, so I thought I'd just bring that one up again just to remind us that was, but the science behind it and the detection of water and the detection that the opacity, or at least the clouds on this hot Jupiter seemed to change over time, and you had this haziness in there. That was all very cool and very exciting.
And let's just not make any bones about it. Like, that is impressive. That you're not just talking about, can we see a molecular species? We're talking clouds here. We're talking haziness. We're talking actual atmospheric characteristics, which is staggering. Indeed. So, let's not downplay that.
And it kicked off a whole, at least a year of worth of James Webb's mission, which was to try and characterize hot Jupiters using these transmission spectroscopy. In fact, it's a dual-pronged mission because they want to not only, of course, find out about hot Jupiters, what more about them, where they come from, all this kind of thing, but they also wanted to really characterize how well James Webb's performance is in doing this transmission spectroscopy by doing the quote unquote easy targets first, right? And then you get a sense of how you do the hard ones.
Yeah. So if you can nail down that as much as humanly possible on the easy ones, only then does it make sense to go and start looking at stuff where you're much less confident, because otherwise you're just pointing really large error bars at something where you've got no hope whatsoever. So I don't know, there could be nothing there. We haven't got the foggiest. Yeah.
So anyway, I thought that would be a nice one to come back to.
Sure.
Now, the other one I've chosen, which is part of the whole planets that will be, I thought, useful to talk about, is another WASP discovery, WASP 43b this time. And this is a paper that came out in April this year, so really relatively new. Remember with James Webb, of course, that the mission's been up for 3 years, but the data are proprietary to those who propose the targets for 1 year.
Okay.
So there's always a bit of a lag.
So the people who put up we would really like to look at this thing, get a year's worth of, we get our hands on that data, and then everyone else can have it.
Exactly.
Okay.
Yeah.
I guess that's reasonable.
So we've always got a little bit of a lag here. So anyway, so WASP 43b was published in April 2024. It was after a campaign which took James Webb continuously about 26 and a half hours. Now, in terms of Space Telescope time, that's a lot.
That's a lot.
That's expensive.
Because there's a lot of people wanting to use this thing. There's a very long queue and a lot of money.
Indeed.
I would have thought being thrown at. I'd like a small amount. I'd like a minute, please. So this is hours.
Yeah,
more than a day.
More than a day, yeah. So, but this is a really cool planet. So it's a hot Jupiter again. But it's one of these ones, I think we mentioned them last time, these ultra short period planets. So this one is 19 and a half hours in period. So less than a day to go around its host star.
Yeah. So if you're watching that for more than a day, you get to see it at least go around like 1.5 times.
Yeah.
Which is pretty good.
Yeah. And this was the really exciting bit. Not only did they watch it for a whole cycle, but they took a spectrum of it every 10 seconds.
Wow.
Yeah.
That's going to improve your stats just a bit.
So I think it was something like they had in the end more than 9,000 images that they were, or spectra that they were using.
Some poor grad student gets to churn through that on their computer.
Well, yeah, some supercomputer perhaps or cluster.
Yeah.
So what they were looking for, first of all, was the phase curve. So remember we talked about that being the difference in brightness as the planet's going around its star, but also looking at the difference not just in the overall brightness, but the difference in the chemical species that you can see going as you go around. Because as the planet, this is a planet that's tidally locked to its host star. So it's always got the same half facing the host star.
Like the moon.
So as it goes around, you see different sides of it, right?
Yeah, okay.
When it's at the back, from our point of view, you're seeing the side of the planet that's facing the host star. When it's at the front, from our point of view, you're seeing the opposite, the side that's facing away from the host star.
Yeah.
And this was really cool because they managed to measure a huge difference between the daytime and nighttime temperatures of this exoplanet.
That I can imagine. I'm struggling to imagine what else you could see, because I would have thought if you're looking squarely at the backside, at the bum of the planet as it's pointing away from the star, there's no light coming from it. So you wouldn't see anything.
Well, no, but you can still get spectrum, right? That's when your transmission happens, your transmission spectroscopy.
Yeah, but isn't the okay? I'm just imagining the transmission happening basically in a ring around the planet. So aren't you kind of seeing the same part?
Yes, but you actually see reflections as well. So reflected light also tells you about the chemical abundances in the planet.
Sure. Okay. I think I'm going to have to wrap my brain around that one a couple of times. But I can, grant you're seeing different things.
Yeah. So they found out that the near side, or the day side of this exoplanet is about 1,500 Kelvin, and the night side's about 860 Kelvin.
That's a significant difference.
It is.
Yeah.
It is. But what's even more exciting...
Both really hot.
Yeah.
Just to be clear.
Yeah, quite hot. Yeah.
Well, 860
Kelvin.
That's
pretty hot.
Yeah.
That's pretty hot.
Yeah, for those of you who need a reminder, we are currently sitting at, about 300 Kelvin here in this room, and the unit is the same as Celsius, centigrade, so that's like 550 degrees.
Oh, yeah.
That's hot.
That's pretty warm.
That's hot. That's pizza oven hot. Yeah.
Okay. So... obviously, temperature on day side, night side, that's quite cool that we can see that. But what got even more exciting was that they were able to measure that they had clouds on the night side version of this planet, but not on the day side.
Right. Is that because it's so hot on the day side that the clouds have got no chance, or what?
Well, partially, but it's also because the solar wind, or the stellar wind from this star is kind of...
just blasting it away.
Yeah.
Yeah.
So they've kind of got rocky and then cloudy.
Rocky and cloudy, and all the clouds are hanging out on the other side.
Yeah.
I'm just going to stay around here. It's scary around there.
Yeah, it's like the atmosphere means that all the clouds condense on the cooler, protected side of the planet.
What a crazy planet.
It's really crazy.
Yeah. But the fact that they can see that, that's good.
I mean, it'd be very interesting. Imagine if you lived on the day side and then going for a holiday on the night side or something like that.
I don't think you'd live for very long on the day side, to be honest.
Well, no.
Mind you, I don't know that you'd live for terribly long on the night side. But yeah, it would be an interesting place. Interesting place for a holiday.
And the final little interesting quirk about this planet is that this is where it gets a little bit technical, but they call it there's disequilibrium chemistry. And what that means is that there's molecules that are out of equilibrium, or molecule groups. And so if you just took, say, like the Earth's atmosphere and just put it in a box and left it for a while, it would eventually reach some equilibrium kind of condition. But disequilibrium means that you're either heating and cooling, so you're changing the molecules that exist, and you're changing the ratios of, say, nitrogen to oxygen or things like that, or you've got production of new elements, new molecules. So actually Earth's atmosphere is also in disequilibrium because we've got, for example, loads of CO2 that we're quite good at making.
We're responsible for that.
Yeah. So that pushes our own atmosphere out of disequilibrium, because if we all stopped, if there was no more CO2 production on the Earth, whether natural or not, tomorrow our atmosphere would change quite dramatically in its composition. So, and you'd be able to detect that. So yeah, it's interesting.
Cool. So there's
something interesting going on, basically.
Yeah, that's the point, is if there's a disequilibrium, that's saying we don't quite know what's happening, but something is happening chemically on this planet.
I mean, thankfully, no one has taken this for a ride and said that there's alien cows farting on this exoplanet, because that would be ridiculous.
I guarantee you someone on Twitter has, but sure, yeah.
But no, that's not at all the point. The point is just more that there's change going on in the system, which is interesting.
And we can detect that is the point. You know, we can see chemicals, we can see chemical species, we can see molecules, and we can see changes in them. Yeah. Which is cool.
Very cool.
Yeah.
So that's WASP 43b. Now the half. This is not truly a new detection or new characterization per se. But it was an interesting article that I read about a roadmap to how we might get to the information that we want.
Okay, it's a promise.
It was a plan, I think. And so this is where we have to take a little step back and remind us what James Webb is doing here. It's really good at doing these hot Jupiters because they're hot and bright and close, and they've got the right temperatures to be sitting in the infrared.
Yes. Temperature is important for infrared. Yeah. That's the point.
Yeah, exactly. And star temperature is really important. So James Webb is really good at looking at very, very cool stars, right? Really cool stars, cold stars even. We call these M dwarfs, and they've got their stars with surface temperatures of less than about 3,000 Kelvin. So our benchmark here is the sun. The sun is about 5,800 Kelvin.
So that's quite cool for a star.
It's very cool. Yeah. So it's almost at the end of coolness.
I was about to say, like, how cool can you get and still be a star?
Not hugely amount cooler than that. But it's very good at looking at these very cool stars, and it's very good at looking at those cool stars when they've got a very big planet. Right. Because the star is small, so the planet to star ratio is very high.
Right. So that's like optimal detection and characterization conditions.
Exactly. Yeah. So big hot Jupiter, small, dim star.
And I'm assuming that the point is you don't want the star to be too hot because it'll swamp what you're trying to look for, which is the characteristics of the planet. Is that the idea?
That and the stars get bigger as they get hotter.
Right.
So the actual size gets bigger, and so the ratio between the planet size and the star size gets smaller. Right. So the detection gets harder.
Right.
So if you look at even like the sun, it'd be much easier to detect a Earth-sized planet around a very small star than a Earth-sized planet around a very big star like the sun.
Right, yes, because you're always looking for what's the ratio of effects. Like, the effect of a small thing on a small thing or a big thing on a big thing is very different to the ratio of a small thing on a big thing.
Yeah. It's a 1% drop, which might be detectable rather than a 0.0001% drop.
Makes sense. Yep.
Right. Anyway, so with that in mind, there's a classic system that was discovered actually during James Webb's sort of construction, which is the TRAPPIST-1 system. And TRAPPIST-1 is by a long shot the best rocky nearby system that could potentially host life.
Okay.
It's the most easy to study one because it's close, because the planets are quite close to their host star. The host star's quite cool, and there's 7 planets, so you've got some good odds there as well.
Sure.
Right?
Okay, so this is a really good system to be taking a look at if you want to just test out your ability to detect stuff around. I mean, is this the point? They're testing out can we find signs of maybe life?
Yeah, well, these are rocky more Earth-like planets, right? So it's looking at, do they have atmospheres like the Earth, which is very, very thin, very, very small? And, are there conditions on some of these 7 that could actually be life-sustaining?
Mm-hmm.
So TRAPPIST was always like, wow, we're so excited to look at TRAPPIST. As soon as we get James Webb up there, we're going to start looking at it.
Yep, that one's definitely on the list.
Yeah. And the problem, James Webb has looked at TRAPPIST-1. It's looked at particularly TRAPPIST-1, I think it's B and C planets, which are the 2 closest ones, and the 2 that are more in the temperate zone of like life, or at least life as we understand it on Earth. The problem is that TRAPPIST-1, the star, it's an M dwarf, and M dwarfs are very tricky in their own right. So we can do transmission spectroscopy, we can get transits, we can get phase curves, but the star is it's not static.
It's not behaving.
It's got huge amounts of what we call stellar activity.
Right.
Okay.
So you've got all the right conditions, you've got the right kind of system, you've got planets in the right place, everything's happy. You've even got the right kind of star because it's not too big and it's not too bright. But is it a characteristic of those stars that they tend to be a bit grumpy?
Yeah, and this is kind of almost the irony of the whole exoplanet characterization game is that the easiest place to go and find these, because you want them to be cool stars, very small stars, as we say, for the planet-star ratio, but also because you want them to be close, because then you can find them and you can see them go around again and again and again and again. If you've got a really hot star, to be temperate, your planet has to be ages
miles away, like us.
Yeah. And you don't have to wait a year until you see another.
Who's got that kind of time?
Yeah, but this is the problem. These M dwarfs are very, very active,
right?
And they do things. They've got spots, chemical sort of spots on this. So it's like the sun has spots, but bigger and like meteor. They've got flares that come off them. So if you imagine you're trying to measure the change in brightness of a transit even, let's just take a simple transit, as your planet starts to come in and block the host star, but then the host star has a flare. So your light goes down, but then it comes up again because they've got a big flare. And then there's a sunspot, and that's a cooler region. Yeah, and so that can come on, and that can look like even more coolness. But then, so there's more dip.
It's almost like they're doing it deliberately.
It is actually, isn't it? So these things are really hard, and they're hard to study because of all this activity. And actually, the activity is chaotic. You can't. It's not periodic like a nice pulsating star.
You can't predict it. You can't sort of. There's going to be a flare in 3, 2. Like that's. It doesn't work that way.
No, and you don't know how big the flare is going to be, how long it's going to last, how much of the surface it covers. Same with spots. You don't know how. You don't even know what the period of the spot is going to be because it depends on where it forms in the atmosphere. So
sounds like a nightmare.
Yeah. So this is kind of a little bit I guess the reason why when we first found TRAPPIST, we were like, yes, this is awesome. We can't wait. And this is why that TRAPPIST is not resurged again in the popular media.
Then all the M dwarf star people just went, think I can see a flaw in your plan here.
Yeah, exactly. So we have looked at it, but it's hard. And this is the problem.
Right.
But what this paper I was reading looks at is basically...
remind us, is the paper from just earlier this year, or are we going to...
it was just earlier. It was in the summer, I think, this year. Okay. I can dig out the details. But it's looking at how you might overcome this, basically, given the situation we're in, and how you might design an observing program that can cope with this kind of variability. And there's a lot of complexity, but the bottom line is we're going to need to do some really large-scale joint space telescope alongside ground-based telescope initiatives to really pull together a huge data set to start to study these things. But the point is we can.
Right.
And we're getting quite close to be able to do something really cool with atmospheres around rocky planets. We just need to work a little bit harder.
So is the idea here that putting it very, very roughly, if you bring in enough data, is it kind of like an averaging thing that if you can average away all of the activity of the star, what you might be left with is what the effects of the atmosphere of the planet.
Yeah, I mean,
because the star's so variable, if we just keep observing it and observing it and observing it, eventually we'll be able to go, that's what the star does. We can subtract that now, and we've got this left. Is that the idea?
That's kind of it. You just hammer it with statistics, right?
Yeah, that's the other way of saying it. That's a much faster way. Just, we need more stats. We need more numbers.
Yeah.
And to do that, what you have to do, not just JWST, we've got to bring in the ground-based ones. Why? Because you want to see different
wavelengths, different resolution.
Yeah. So it's just a problem you just got to throw all the telescopes at.
That's basically the summary.
Yeah.
Let's just throw everything we have.
Yep.
This is the only system that we've got even a chance of doing it with right now. There's nothing else that even comes close.
This is the only one.
It's the only one. It's because it's so close.
Yeah.
There's just no other examples of rocky
so if
systems
we can't
like
get
this
one right, like this is our test bed, right? It's not that everyone's pinning their hopes on, we'll find life. No, that's not the point. The point is, if we can't test it out on this one, like this is the good one. So if we can't do this one, back to the drawing board.
Yeah, this is the hot Jupiters of rocky planets.
Right. Okay.
But yeah. But it's exciting that it's possible because I think for me personally, I've always gone full circle. It's gone from TRAPPIST is going to be amazing, James Webb is going to tell us everything about it, to
TRAPPIST is a bit of a problem, actually.
Yeah, this is actually really hard. Yeah. Maybe we're not going to get much out of this, to actually there might be a way if we're very clever and we put a lot of energy into this.
Right. So are they talking in terms of like, here's a program, here's how we're going to do this, or is it more, we could kind of wander in this direction. We'll need more people on board. Like, what are they actually proposing?
Yeah, it's a bit of an observing strategy. So instead of doing maybe like what was done with WASP 43b, where it was just stop and stare at it, maybe we can make that more efficient use of that time and do more intermittent observations of the system, things like that.
As well as you say, bringing in other telescopes in other places down on the ground as well.
Yeah.
Cool.
So I think the bottom line of just it probably is possible is exciting.
That's enough to ramp up the excitement again. So we can do this.
Yeah.
That's really cool. I like it. So, all right, Emily, you've given us two and a bit, 2.5. I'd give that at least a half.
Yeah.
I'd say 2 2/3.
Yeah.
I think we're on the way there. 2 and a bit. Ways that JWST is actually up there doing stuff, helping us to understand, characterize planets, exoplanets around other stars. Awesome. Okay. It's kind of where we are now. So JWST's, we hope, got a reasonable life ahead of it. Like it's up there. We want it to keep going. So what's next? What's coming up?
Well, the good news is that the primary mission, so this is like the minimum mission requirement for JWST, is 5.5 years. We're coming up 3 years into that, and it shows no signs of stopping. So that primary mission is going to be easy.
Blown away. Yeah, things aren't falling off yet.
Currently, we've got 10 years of JWST planned. So we know kind of what we're going to do. And everything seems to be working really well. So actually, currently, it has a life expectancy of around about 20 years.
Okay.
So that's nice.
So the mission parameters are generally kept fairly conservative. You know, we'll get it up there. We'll do it for 5.5 years. But in reality, everyone's kind of going, it seems to be working all right. So let's do 10, that's 20 years.
Yeah. And I mean, this is true for many other missions, right? I mean, Hubble is coming up 34.5 years old.
Still going strong.
And it's still going strong.
Yeah.
Think about some of the Mars rovers that just went on and on and on. Not all missions do this, right? Kepler, for example, actually lost its reaction wheels a little bit earlier than we hoped it would.
The wheels literally fell off,
a little bit. But it met its minimum mission requirements. So it didn't do huge amounts more than that.
Yeah.
So, you kind of luck of the draw in a little bit.
Yeah. And I mean, it makes sense. Like, you don't want to send JWST up there going, it's going to be great for 20 years, and then find that in 6 years' time, the main thing's fallen off and it doesn't work anymore. It's better to go the other way around. Promise small and then hope for big things. Yeah.
It's a different type of engineering, isn't it, to make something that you cannot fix. That is it. It's gone. And you've got to make sure that it's as operable as it can be for the next 10 or 20 years.
With Hubble, we could did go and tweak it, didn't we? Wasn't there a problem very early on with Hubble that it needed someone to go and just sort of tighten up a bolt or something?
Yeah, its mirror had an aberration, so they needed to go fix the focus of the mirror a little bit.
But I mean, that wasn't like done through software. Like they literally had to grip onto the thing and go tweak. That's not possible with JWST because it's somewhere else.
Yeah, that's a long way away.
It's a long way. Just remind us where JWST is.
It's at Lagrangian point 2. That is kind of, it's a special little gravitational sweet spot that's quite far away from the Earth, but sort of balanced out between the Earth, Moon, Sun, Jupiter.
Yeah.
So
but just remind me, when you say quite far away, like the Moon's quite far away from the Earth, the Sun's quite far away from the Earth. Like lots of things are quite. So in terms of those kinds of distances, just how far away?
Much further than the Moon. Not as far as the Sun.
No, okay, somewhere in between. But much further than the Moon. Like it is a long way away.
Yeah, so and it tracks around with us as we go around the Sun. Yeah, that's the magic of the Lagrangian point.
So we can't just, whack a spacecraft up there. Not even Elon Musk is going to do that. No, that's far beyond. God. I mean, we've even NASA's been very clear that there will be no more missions to Hubble, right? That's it. And that's the easy one.
I think that was 2009.
Something like that.
I think was the last crewed.
If Hubble goes down, it's junk.
And to be fair, it's done all right.
Yeah, and I think that would be okay. I think
I would be okay if
But
Hubble
the point with JWST
retired.
is if something happens at this point, only 3 years in, so, it's just too bad.
I think we'd be quite cross.
Yeah, you'd be a bit annoyed. But getting back to your point, which was people are planning out to 10, 20 years worth of data taking. We've got a lot ahead of us.
We do.
So tell us about that.
Well, I don't really know. Honestly, I can't tell you what 20 years' time exoplanet science is going to look like.
A lot could happen.
20 years ago, it looked very different. 1996, we had like one exoplanet around
a good point.
a sun-like star.
Lot can happen in 20 years.
So
we've gone from one exoplanet to we're actually literally looking through their atmospheres.
Yeah.
That's pretty good.
So I would not even hesitate to guess.
Fair enough.
What it would look like in 20 years' time, but I know it's going to be awesome.
Well, Emily, as you say, there's plenty to look forward to if you're a big fan of JWST. Don't look away. We've got lots and lots of data to come. Who knows where it's going to go in the next 5, 10, 15, 20 years. Huge amount can happen over the next couple of decades. Got any best guesses? What's going to be the next big milestone for exoplanet science?
Oh, this is actually better to ask an astrobiologist.
Yeah, but I haven't got one. You're here.
It'll be whatever the special magic combination is of molecules in an atmosphere that tells you you've got life.
Ooh, you reckon that one's...
what that special combination is highly debated. But
I mean, that's a really interesting question, isn't it? Is like, what's the time scale for us actually being able to get something like that? It's really interesting. Lots to get excited about ahead. Listen, Emily, if people wanted to write in and talk about how excited they are for the future of JWST science, how could they possibly do that?
Oh, I think they could head along to syzygy.fm, so syzygy.fm.
Why? What's there?
There's a little contact us page. It's actually quite a big page. It's got a big galaxy on it.
Yeah.
And you can click on that and
if you're going to have a website for an astronomical podcast, it should be covered in nice images. That was my design principle.
Yeah, I noticed you didn't choose WASP-96b as one of your backgrounds, though.
Well, I could change that.
No. Just don't.
Okay. Point is... People can send us stuff through the webpage. Just go and find it. And while you're there, you can listen back on all the other episodes and have a look at all of the other pretty images that we've got with them.
We did a reaction, I think, to the first 6 images of James Webb.
We did.
So that might be an interesting one to go back and look at.
That would presumably be, when was that? Like mid-2022?
I think it was after I came back, after my break. So, yeah.
Look, go and find it. You people are resourceful. Go and find that one. It's definitely worth a listen. The other ways that you can find us on the interwebs are through various social media. We're not on Twitter or X or anything like that. But, Facebook and Threads and Instagram and so on. We pop up from there from time to time. And at SyzygyPod is where you can find us there. If you want to support the show, just listen. Keep on listening and tell other people that you're doing that. Bring them along for the ride and tell them there's this great podcast and they talk about awesome things and you really should listen, because that helps us to rise up through the noise, as does you leaving us a review. Go to your podcast player of choice or website and leave us a couple of stars and a few words, and that also helps us to get through the noise of the podcasting universe. You can become a financial supporter of the show over at patreon.com/syzygypod, where you can throw a couple of pounds, a couple of dollars our way every month or so to help us keep the electrons flowing through the website and to help us do the things that we do here on Syzygy. Speaking of the things we do, we'll be back again in a couple of weeks for the penultimate episode of this series. So until then, Emily, catch you later.
See you later.
Bye, everybody.